So I want to talk about routes to low-carbon vehicles for a relatively small Jaguar Land Rover luxury vehicle manufacturer. What I'm going to start off by just talking about is our portfolio of products. So, here are some of them. This is the F-Type. You can see the XFR there, running in quite an interesting mode. These are some of the Range Rover and Land Rover vehicles undergoing some of the environmental tests that we have to put them through to make sure that they meet our customers' expectations. Here we have some of those vehicles testing in Ogiplog in Sweden, and off-road, including things like wading and all these sorts of things. So there's a fairly sort of comprehensive series of things that we have to put our vehicles through. And the reason I'm sort of going through this is really buying a luxury vehicle is very much an emotional purchase. You're buying into a dream. Many customers won't use these sorts of capabilities of the vehicle, but when they buy the vehicle, they expect them to be there. This is just a short video to just show some of the testing that we carry out on our Range Rover vehicles. Great fun if you get a chance to do this. It's fantastic. And regardless of what we use to propel those vehicles, customers don't care. They expect the vehicles to be able to do this. They expect to be able to take their vehicles off-road. They expect to be able to take them around the track. They expect to be able to drive them in a spirited way. The customer is king in this respect. And this is what our showroom looks like in 2014. Everything from Range Rover Sport, the F-Type, the Evoque, lots of very, very upmarket, very fantastic cars. And that's been reflected under Tata ownership with, over the past 4 or 5 years, massive sales growth for our brand. And I've been with Jaguar Land Rover for 25 years, and I've got to tell you, it feels like a completely different company. A completely different company to how it was when I joined. Tata's a very unusual company under its stewardship. It reinvests a lot of the profit that we make back into the product and allows us to make really good products and carry out research into some of the advanced technology areas that we need to for the future. So this is the problem. You've all seen graphs like this that the Earth's taken millions and millions of years to lay down the reserves of fossil fuels of oil and gas that our society is based on. And we're having a party. We've used that up in about 150 years. I think if you project yourself 500 years into the future and look back, this time is going to be looked at as a time when mankind just used up was profligate with the world's resources and used them that. So that's got to change. You've got to move into that sort of renewable area. And if you look at the sort of various forms of renewable energy, it's just a matter of timing. We can't afford to wait millions of years, so we have to look at the various routes that give us the fuel that we need for transportation in a reasonable amount of time, and we have to use that more efficiently. This is what the sort of world regulatory landscape looks like in CO2 terms. The interesting thing to take out of this graph is that everything's converging in 2020. And 2020 is the products that we've got in the product development machine now, converging to around about 100 grams. And that's 100 grams per kilometre over a particular cycle. Now, that's only the start. We can't sort of sit on our laurels and wait, because in 2030, that's probably going to be something between 60 and 80 grams. And there's going to be relentless pressure down to keep pushing the CO2 emissions down on the vehicles that we manufacture. I'm always very nervous about making predictions, because I can always guarantee that any prediction I make is going to be wrong. But I think that what we're going to see is petrol and diesel usage falling gradually, electric vehicles and hydrogen, that sort of share growing over the next sort of 30 or 40 years. liquid fuels are going to continue to be the majority fuel, and yeah, there'll be a sort of an influx of biofuels. Probably the second generation biofuels will come in. And it's quite interesting to listen to some of the synthetic processes that have been proposed by some of the other speakers. So I'm going to talk a little bit about the electric vehicle elements of this. So if I look firstly at what a vehicle manufacturer can do to reduce the energy consumption of its vehicle, we've really got three sort of pillars, three sorts of things that we can look at. The first thing is we can take weight out of the vehicle. So you take weight out of the vehicle, whether it's a human being or a vehicle, you become more agile, you can sort of run faster, do all those things. So taking weight out is a good thing to do. You can also reduce parasitic losses. A parasitic is probably it's a bit of a misnomer, but it's the losses that you get from running the vehicle along. It's also your hotel load, so the energy that you use to heat and cool the vehicle, the energy that you use for the lights, to clean the windscreens, all those sorts of activities that keep the vehicle running. And then you can look at powertrain innovation, which includes hybrids. And I'm going to touch on hybrid technology in a moment. So you can make your conventional internal combustion engines burn fuel more efficiently, you can reduce the losses in the powertrain, and you can generally improve that propulsion system on the vehicle. Now, there's absolutely no point in doing any of that unless you think about the life cycle of the vehicle. It costs you a certain amount of energy to manufacture your vehicle, a certain amount to use it, and then you've got to dispose of it at the end of its life. And all those activities take a bit of energy. So you have to consider that whole life cycle. There are some interesting challenges there for electric vehicles, which I think are eminently solvable, but we need to be thinking about them. So just looking at weight reduction, we've gone aluminium intensive on the Range Rover, which we just launched. We've saved over 420 kilograms by going to aluminium and going to lightweight engines. We're very much advocates of clean diesel technology. Every 100 grams that you saves about 2% in weight in fuel consumption, and it also means the vehicle's more dynamic. It feels nicer to drive, which is one of the reasons why we've gone to this aluminium-intensive technology. So if I look at the standard Range Rover that we've just launched, these are some of the things that we've done just to improve that basic vehicle efficiency. We've gone for improved aerodynamics, we've downsized the engine, we've gone for low rolling resistance tyres. Incidentally, one of the things that my team told me to tell you is that the test work on that video you saw earlier on was done on standard tyres. It was done on standard low rolling resistance tyres. So if any vehicle dynamicists in the audience, they'll probably know what that means. So we've also gone for 8-speed transmissions. We've also gone for scavenging electrical energy from the dyno. So a whole sort of set of things which are really around conventional vehicle optimization. If I then look at, so this is one of the previous panelists talked about the Automotive Council, and this is the low carbon technology roadmap. So this looks at the various things that we need or we are planning to do in research across the vehicle to improve CO2 consumption. So you start off right at the bottom and you can see the conventional optimization, vehicle weight and drag reduction, and optimizing standard transmissions. Then you start to go to some of the more advanced technologies, the things like micro-hybrid, full hybrid, plug-in hybrid, right the way up to electric vehicles and fuel cell vehicles. We have a partnership with government, what's now Innovate UK, but was the TSB, to develop some of these technologies. So now talking about the hybrid, one of the things I need to emphasize is I need to go back to the beginning and talk about particularly the Range Rover and just refer you to the things that vehicle is expected to do. It's expected to drive nicely, it's expected to have full off-road capability, it's expected to wade. So this is a Range Rover first and a hybrid second. So in order to put, this is a parallel hybrid 35 kilowatt crankshaft integrated starter generator, a 1.4 kilowatt hour lithium ion battery integrated underneath the floor. Now it's integrated under a boron steel armor plated plate, so you can rock crawl this vehicle. That plate will take the full weight of the vehicle coming down, and it's indescribable what some of our engineers will do to these vehicles to test them. It also weighs to nearly 1 meter. That was, and this is a 300 volt system. So you have to think about the level of integrity that we have to put into the systems in order to achieve that. And this is what it's done for us. We've got 169 grams per kilometre vehicle, which is fantastic for that size of vehicle. Similar performance to the V8 in terms of acceleration, so 6.9 seconds, 0 to 100 kilometres per hour, as opposed to 6.8 systems. And this is the sort of our first step on this journey towards electrification. Okay, slightly complicated slide here, but I want you to sort of think about the notion of splitting the vehicle between the propulsion system and the vehicle system itself. And if you put a vehicle through a particular cycle, it takes you a certain amount of energy to push it through that particular cycle. So I've shown two cycles there. The one on the left is the NEDC cycle. The one on the right is on the left-hand side of the slide, those two top graphs. The other one is the urban Artemis cycle, which is a real-world cycle. So you push the vehicle through that cycle, and it takes a certain amount of energy. And the two graphs at the bottom show that that's correlated to weight, and that second graph shows the difference between a real-world cycle and an emission cycle. This basically shows your weight along the bottom and your energy consumption on the vertical axis. So you take a particular vehicle, and it's a particular weight and mass of vehicle and characteristic vehicle. It takes you a certain amount of energy to push it through a cycle. You then treat the powertrain system completely separately. It doesn't matter what that propulsion system, what that powertrain system is. It takes a certain amount of CO2 to produce a certain amount of energy. And so this gives you a way of looking at the vehicle energy consumption and the propulsion system consumption separately. I've done a very simple calculation here on an electric vehicle, which I've based on European grid averages and Norway's grid average, which was the lowest I could find. So if you work from the left, you've got a generation system that's generating power. And the European grid average for generated power is 352 grams of CO2 per kilowatt hour, so 0.352 grams per watt hour. If you then look at a typical electric vehicle, something with a 22 kilowatt hour battery, that takes roughly 129 watt hours per kilometre to push it through a cycle. That's an emission cycle, that's an NEDC type cycle. If you work those calculations through, that comes to 51 grams per kilometre on European electricity. That's pretty good, actually. That's quite a good sort of... That's not the whole story. If you then look at the amount of embedded energy in the battery, that's about 10,000 kilowatt hours. So again, if you use that figure of European grid energy, then you've got that and average that over the use cycle of an average user who drives 146,000 kilometres during the lifetime of the vehicle. What that works out to is 25 grams per kilometre on top of that. So you then get to 76 grams per kilometre. Still good, but it's not quite as good as it was before. So one of the things we have to take out of this is that it's essential to decarbonise the electricity grid to make to really reap the benefits of electric vehicles. Brief discussion on research activities. We've got a long history of research activities that we're carrying out in collaboration with a number of partners, starting off in 2006 with Leander, which was a parallel hybrid, REHEV, a range extended hybrid electric vehicle, which was also a conventional hybrid. Then moving on to Range E, which is a Range Rover plug-in hybrid, and Revolution, which was a range-extended electric vehicle. And we did those really in collaboration with government and with with various partners, mainly in the UK. What that led us down to was that the energy storage element of this is really quite an important thing. So we kicked off the Catapult energy storage activity in collaboration with Tata and with WMG, Warwick Manufacturing Group. And that outreach is to a number of universities around the country, the UK and around the world, and is really looking at the whole energy storage side and how we improve that. Really vital to make sure we have viable electric vehicles for the future. We've also looked at some more extreme things like CX-75, which was a downsized sports car, very nearly 1,000 horsepower vehicle, an extreme sports car. Then our latest project is Evoque-E, which is in collaboration with the TSB, which is looking at much more of a modular system, much more something that we can start to move towards potential production solutions in the next few years. Full electric, full battery electric vehicle, plug-in hybrid, and the next generation, a mild hybrid. We're applying a whole sort of range of technologies across those cars. So a few closing remarks. Luxury customers, they're not going to compromise their requirements. They're going to want cars that they can drive, cars that are an emotional purchase, cars that sort of fulfill their dream. Fossil fuels are going to be, and actually that's going to be quite challenging to us to make sure that we can do sustainable vehicles which are fun to drive, which are great to drive. Fossil fuels are going to be around for a while. Obvious, we need to make the best use of those. And even when we move to some of the more sustainable fuels, there are going to be less of those around. So we have to make more and better, more efficient use of those. We've got plans to drive down CO2 emissions, as well as lifetime CO2, and electrification is a key enabler for doing this. Thank you very much for listening.
Thank you very much. So moving on to the second speech, which is Dr. Nam Su, who is the former president of the Korea Advanced Institute of Science and Technology, which is the first and top science and technology research university in Korea. And he's going to present how we can save at least 30% of oil through the electrification of ground transportation systems. So again, we've got 15 minutes with the clock showing there. Thank you very much.
Thank you. Good morning. It's a pleasure to be here. About now 8 years ago, when I went to KAIST as president, we decided that KAIST should do something for humanity by solving some of the major problems of humanity in the 21st century. So we took on this idea of dealing with energy, environment, water, and sustainability. So as part of this initiative, we have undertaken a number of different projects, and one of those projects is the one I will be talking about today. It is to reduce CO2 level by having entirely new technology adopted rather than continuing to use internal combustion engines from our cars. So how can we reduce CO2 emission and deal with global warming issues? And a number of speakers talked about very interesting ideas they're all working on, and they're all somewhat different, and ours is different as well. The answer to the CO2 problem is fairly simple. Reduce consumption of fossil fuels, such as coal, natural gas, and oil. If we don't use those things, then we won't have CO2 problem. The question is how you do that. It turns out that two major sources of CO2 is ground transportation system as we all know, and then electric power plants, especially those that use coal. Again, fairly simple answers to very complex questions. So what's the solution? The first solution to the first problem that has to do with transportation is electrification of ground transportation systems, not only cars, but trains, buses, and so on and so forth as well. We call it EGTS. And then solution to electric power plant is green electric power plants, namely the ones that do not emit any CO2. Ultimately, that's the solution. But can it be done? It turns out that if we go EGTS, according to very rough calculations, we can reduce CO2 emission by about 30%, and we can reduce oil consumption somewhere between 30 to 50%. That's a substantial amount. It turns out that, as a number of speakers talked about this already, we are using great deal of oil every day, 92 million barrels per day, depending on which numbers you look at. And then 70% of this oil is used to power our vehicles, IC engines. In case of Korea, consumption of petroleum is mostly for vehicles as well, about 70%. And the US, in the case of US, total consumption of petroleum, I guess, is about 19%. US consumption for transportation of the oil that we use is about 71%. And so all these things, numerical numbers you already know, so I'm not going to belabor the point. The point is that we are using mostly petroleum for transportation. And petroleum is not used very much for electric power generation. It turns out that in transportation, most vehicles that we use today are IC engine-based, and the problem is CO2 emission. The second problem that we are all aware of, but haven't talked very much about, is very low fuel efficiency of IC engines. Depending on the numbers you see, well-to-wheel efficiency of IC engines is very low, 17% or less. So a great deal of chemical energy we put into our cars and whatnot do not really go to the wheel, but it's wasted. And you look at internal combustion engines, it really defies thermodynamics logic in the sense that thermodynamic efficiency should be higher with a higher temperature, but we cool these internal combustion engines because we cannot deal with lubrication problem at higher temperature. So we cool it and we lose energy, and it's sort of an ideal design that we have. But most IC engines, most cars use IC engines, and a number of speakers talked about ways of making it better, use different fuels, and so on and so forth. Our approach to this was just get rid of IC engines altogether from our vehicles and use electric motor. We already have that on the road today because we have electric cars running around in a number of different cities, nations, and so forth. So what's the problem with that? The problem with that, all battery-powered vehicles, as many of us know, when we use a large number of batteries to power our vehicles, the weight of the vehicle goes up. In the case of bus, weight of bus doubles because we used so many batteries. They are expensive, heavy, bulky, large, and long charging times, and then efficiency of battery itself and the life of batteries. And also safety is an issue. We never talk about this. But when you have a lithium batteries, essentially you have fuel and oxides together in the same package, and then those things can explode if you puncture it, And obviously, we want to design it so that these things do not happen, but they can happen as well. And obviously, finite supply of lithium, so people are working on sodium-based batteries and so on and so forth. Our solution is wireless supply of electric power to the vehicle. So battery itself, the car itself has a small battery on board, but primary energy source is the externally supplied electric power. And I'll show you a videotape of actual bus running commercially in Korea. And they are very efficient, and the additional weight is very small because we use about 1/5 the size of battery normally used in these vehicles. And people often wonder how you're going to supply electric power everywhere, but it turns out that by having small battery, only 5 to 15% of the road weight needs to have this underground power supply system. So the cost of that power supply system is not that much. When we calculate the numbers, it's far cheaper than diesel and natural gas. It depends on the nation because the price of these natural gas are all different. But when we calculate this, in fact, the actual operating cost of buses running in Korea shows that the cost of supplying electricity is about 20% of that of the cost of using natural gas by comparing the run distance and so on and so forth. There are two basic technologies that we invented. One is called SMFIR, Shaped Magnetic Field in Resonance. Essentially, it's a way of sending power over a large distance. It's interesting that many of my own colleagues, as well as others, thought that cannot be done. You cannot send 100 kilowatts of power over a very large distance, supplying it from underground supply system. And we demonstrate that we can design it such a thing can be done very efficiently, it turns out. Second thing is using this SMFIR technology and then building a vehicle that actually receives electric power wirelessly and then move around. SMFIR, this is the simplest way I can explain how the technology works. Essentially, it has a North Pole and South Pole. And then to reach certain high level, we control the distance between North Pole and South Pole and create electric field. So farther apart the poles are, higher we can reach. And that's a simple way of explaining it, but it says essentially that's the basic ideas. So we developed all these, and I must say we did it in a very short time. From the inception of the project to actual implementation of the road, taking passengers around took us 2 years. And that's one of the things that I've been trying to teach our students. That is how you design complex systems without trial and error process that typically many companies and others do not go through in developing these complex systems. We develop a number of different complex systems, but it doesn't take that long if you do not make a mistake. And so we teach how to do that. So it has been installed in Industrial City Gumi and Seoul Grand Park and KAIST campus. And these buses have been running around for 3 years without any problem. The driver does not have to do anything other than drive because he does not have to charge the battery. Battery is charged while the vehicle is moving, and therefore you really do not have to be stationary to be able to recharge the battery. So this is the bus actually in operation in Gumi City. There's an industrial city where semiconductors are made. And so I have a small video clip, maybe I can show, and then shorten my presentation by actually showing that. So when you look at the cost, by the way, this was selected as one of 10 emerging technologies by the 2013 World Economic Forum. It was also chosen by Time as one of the 50 major inventions 2010. And we are hoping that it can be installed in the US as well as in Europe and elsewhere. These are comparison of IC engines and whatnot. I had only 15 minutes, so why don't I stop here and ask if you can show the videotape. So we did all these calculations, and it shows that well-to-wheel efficiency of electric drives is about 30% or more, 35% or more efficient than IC engines. That's quite a bit. It'll be very hard to beat that by any other means. And we also made a cost comparison. Is the video tape going to roll? To show exactly how much it costs. It's interesting. We have this, the bus route, and it's about 35 kilometers round trip. And using CNG, the fuel cost is $20.58. Electricity costs $3.92. And we are also trying to develop much higher, the high-speed trains. High-speed train in Korea is running at about 300 kilometers an hour. We're going to go up to about 400 by getting rid of all these catenary mechanical contact, sliding contact to deliver electricity. We do this from the underground, and we can deliver 1,000 kilowatts of an hour at each power pickup unit, and that's being developed as well. So we compared the cost of our system versus cost of using a CNG system, and cost is quite favorable. And again, these comparisons will be different in different countries. And in the US, the natural gas is much cheaper, and therefore the figures will be different. But rough calculations sort of indicate that still even in the US, electric system will be far cheaper. People often wonder how many power stations, electric power stations you need to have to replace all IC engines in Korea. According to very rough calculation, if Korea builds 2 more nuclear power plants, then Korea does not have to use petroleum to propel automobiles. Two more nuclear power plants. Korea right now has about 21, I believe, nuclear power plants, and they're building more, but they devote 2 of these to replace gasoline, then Korea can run. And 1/3 of Korea's import is for the fuel, for petroleum, and then Korea can eliminate that. So these are the kind of things that we've been doing, and I thought you might be interested. Is it possible to show that the video clip? No?
The world's first wireless online electric vehicle has begun its first test run here in Korea. Developed by Korean researchers, the new technology will likely bring about a revolution in the electric vehicle market. Our Kim Min-ji has more.
The vehicle rolls down the road just like any other bus. But as it approaches the bus stop, it begins to charge itself automatically. The online electric vehicle receives power through shaped magnetic field and resonance technology that enables the bus to transfer electricity from the road while in motion.
The bus is able to charge itself as it passes over parts of the road that have charging facilities installed. The bus then can travel on its route with a charged battery.
The power comes from electric cables buried underground, creating magnetic fields, which the bus then converts into electricity. The bus's battery is only 1/5 of the size of the battery on regular electric buses and can receive 100 kilowatts or 136 horsepower of electricity at a 75% maximum power transmission efficiency rate. Moreover, the charging facilities are not expensive to install, and the vehicles can be charged while stationary or while in motion, making it both quick and economical. Developed by researchers at the Korea Advanced Institute of Science and Technology, the wireless online electric vehicle has also been listed as one of the world's 10 most promising technological developments by the World Economic Forum. For now, 2 buses will operate in a test run on a 24-kilometer bus route in the city of Gumi in North Gyeongsang Province.
The pilot program will run until the end of the year. Next year, we plan to get government support and expand operations. This new technological development will likely replace transportation worldwide.
The government hopes that the commercialization of the new technology will give the country a boost in the electric vehicle market. Kim Min-ji.
Thank you. The goal of Gumi City is to have all their public transportation systems replaced with this electric bus. It obviously depends on whether or not they can secure the budget and so forth. But they'll be continuing to replace existing buses with electric buses, and hopefully other cities will adopt them as well. And we are also working actively in the United States, hoping that we can begin to install some of these systems and show people what can be done. Okay, thank you very much.
Thank you very much. I now invite Professor C.C. Chan, who is the Honorary Professor at the University of Hong Kong. He is a Senior Fellow at the Institute of Advanced Sustainability Studies in Germany, a Fellow of the Royal Academy of Engineers in the UK, an academician for the Chinese Academy of Engineering, a founding president of the World Electric Vehicle Association and Electric Vehicle Association of Asia Pacific, and finally a founding director of the International Research Centre for Electric Vehicles. Please join me in welcoming Professor Chan. Thank you very much.
Thank you so much, distinguished guests, ladies and gentlemen, friends and colleagues. I am honored and privileged to be here to share with you my humble experience over 4 decades in research, development, and promoting electric vehicles worldwide. I only have 50 minutes. Originally, I have 120 slides, and now I reduced to 80. It's still too much. So what should I do? I just give you what is my key message, and then I will run with very small or without elaboration, so I can keep the 50 minutes. Okay. My key message is, first, we are now in the eve of the commercialization of electric vehicles. As I said, I started 40 years ago. At that time, it's research, development, but now it's in the eve of commercialization. That is, the train of the commercialization is taken off, but we are still in the very early morning. Still many challenges. So what my key message, we need to build a new paradigm. It is not just a car. It is a new paradigm. Means we would like to have good product, good infrastructure, and good business model, so that the user can afford it, convenient to use, and confidence to use. First message. Second message, in order to build this new paradigm, we need good 3 partner relationship. That is government, industry, and market. Thirdly, what is the bottleneck? Today, the bottleneck is not the technology. The technology is there and improving. The bottleneck is innovative policy. This innovative policy is to form the paradigm. That is 2 giant industries. One is the energy industry, if you use electric, that is the power electric industry, and the automotive industry. This is 2 giant industries, but facing new problems. Because electric car is no more mechanical products. Electric car is disruptive industry. Electric vehicles, in terms of function, it's no more just a transportation means. It is a moving energy storage. In terms of production, electric vehicle is different. Conventional car, you have 20,000 and you must 20,000 or 30,000 baht, and you must pick an empire. Closed house. Electric vehicle only a few thousand. You can be open house, modular. So the production is different. How to make the 2 giant? Yeah, electric vehicle is no more conventional vehicle. And from the power system, electric vehicle is no more conventional electric load. It is new type of conventional load, and you can friendly interface. So how the policy can the 2 big giant, the energy supplier, the power, and the automobile shake hand. And therefore, if we need open mind. That is why my topic is Renaissance first. Renaissance spirit is open mind and have the courage. Okay, civilization. If you look back of the civilization, in the old days, we can start from China, Syria, including Israel also, and then move to the West. But after the West is ancient time in China for discovery. But in the West, Renaissance, open mind. Then move to the West, from Europe to East Coast, from East Coast to West Coast. This will continue and coming back. In fact, my president Korea already have sample. Come back again. Okay. So now, We must open mind. How to open mind? We take account of the Oriental spirit and the Western spirit. The Oriental spirit is I Ching. In fact, it is also represented by the national flag of Republic of Korea. What is I Ching? I means change, but when we change, there's principle. What is the principle? When you change, it's a periodical. I'm doing electric vehicle for over 40 years, and I see electric vehicle up and down. The change must be periodical, must be balanced, must be unity of opposite. You can see in the left side, it is straightforward thinking. White is white, black is white. But here, like the national flag of Korea, half is white, half is black, but it's curved. Black can be changed to white. White can be changed to red. Inside the black, there is white. Inside the black, white is black. That is holistic approach, dialectic approach. Okay, so in terms of Western, we should learn from the Renaissance. This is a typical work by Michelangelo. Before the Renaissance, a Spain painter paint beautiful ladies, and it was hung because it's against the religious. But now this is everywhere. And we must learn from Da Vinci. What is the Renaissance? The Da Vinci is a great engineer. He made the model of the aircraft. He also a great doctor. He did sections, and he also a great artist. Okay, so what is Renaissance? Open mind. Closed mind cannot change. We should soar beyond what was and to see what is. So what is resonance scientists, engineers? Scientists are answering why, and engineers answering how. So resonance engineers should have sub-features. First, global thinking. Second, harmony thinking. Third is circle thinking. Circle thinking, you must look all around. But as my predecessor said, battery, you must also look at the battery safety. You must look the circle. Third, that is closed loop. You must not open loop, close. You must see the feedback. That is life cycle, 3R thinking, reduce, reuse, and cycle. EV developments. Mobility is a medium. Mobility is the most apt expression for our happiness. This is when I founded the electric vehicle in 1988. I'm still young, in the middle. When I saw in this car, I'm very touched. Because some of them now is already in the heaven. Some is on the sanatorium. Some is fully retired. I asked my Brugialino, my Italian is retired. But I'm touched because my colleague in US, Dr. Vogt, before he passed away, he asked his son to call me. Just Sisi, you must continue. So I'm already over almost 80. I still continue here, in Tel Aviv, to share my experience with you. Okay. So as I said, today the key is how the government and industry and market work together, and how the good product, good infrastructure, and good business work together. Okay, so this is one. Okay, so that is the example. In the convenience car, you need 30,000 parts, and you must build empire, like in Detroit, in Changchun. Electric car not necessary. You can use a modular because you can use a de facto standard, open house standard. We should learn from the history. As I say, mobility is a freedom. Mobility is happiness. Our mobility originally is use a horse, and then when invent the steam, put there, but people don't like it. It's dirty. When Faraday invented motor, Watt invented battery, you put there, people like it. Later, 20 years later, the ICE comes, people still don't like it. Because at that time, electric vehicle is cheaper. Because at that time, it's handmade. Electric vehicle easy to use, particularly the ladies, because it is easy to drive. Not like an SUV, you must use a crankshaft. So you can see that typical lady. The lady can drive electric vehicle very easily and chatting with their boyfriend. But if you use ICE, you can stuck if you forget to save the gear. So it's very popular. But who changed the world? Ford changed the world. We must learn from Ford. First, when he built the assembly line, reduced the ICE. Secondly, he talked to the oil giant. When at the beginning, there's no many gas stations. Now we feel, where is the infrastructure? But you think at that time, for there's no infrastructure. But he talked to the oil giant to set up the infrastructure. He take the market. He asked his employee to buy electric car. Okay? So three goodness, good product, good infrastructure, market. We should learn from Ford. Then, in 1932, electric vehicle died. The last electric company, they thought electric bankrupt. Okay? Is this my Okay, so I must be quick. Okay, so there are three key technology. Three big electric motor, battery, controller, three small electric steering, electric air conditioning, electric braking. Now, EV global everywhere. Now it's 500,000. US is number 1, 200,000. Japan number 2, 300,000. But China number 3, but only several 10,000. This is the listing. Because I understand my PPT will be online, so you can read after my speech. But in per capita, Norway is number 1. In per capita, Norway is number 1. But today, you see, in Norway already, you see, in Norway is 4%. Every 1,000, you have 1 electric vehicles. Okay. Now, China EV development. China is a big country. I show you this first. In the 1950, if you go to Beijing, you can see a blue sky. But now, if you go to the Beijing, you cannot see the blue sky. But in the 50s, if you go to Cambridge, the London, you cannot see the London Bridge. But today, you can see London Bridge. And what is the price of China? China has a lot of money, input oil. Now it's 58% of oil is import and cause national energy security problem. And then the sky is gray. That is the China cause. Why? Very simple. Because China GDP is still growing. Electric vehicle, car volume is still growing. You know, the automobile industry has a rigid rule. It is linked with the GDP. The GDP growing, the car is growing. So China now, the other rule is that high growth, steady growth, and flat. In the Western world, already flat. But China, steady growth is finished, but steady growth. High growth already finished. High growth is 30%. Now it's steady growth, 10 to 15%. Will continue in the next 10 years. If all this car propelled by oil, China hopeless. So the President Xi Jinping asked the Chinese Academy of Engineering to draw a roadmap on the energy generation and revolution, energy generation and consumption revolution. And the subtopic is electric vehicle, asked me to head it. So my research team has projected. We have 3 phases. Phase 1, from now to 2020, we focus on bus, taxi, logistics car, penetration 2%. Now it's only 0.3%. And our objective is reduce the PM2. The second phase is 2020 to 2030, and mainly is conserve the oil and hopefully 10 to 15%. Third is reduce the CO2. Hopefully at that time the hydrogen is there, then can run for 50%. And President Xi Jinping has some agreement with Obama 2 weeks ago. That is, the China will be 2030 will be the ceiling. My group do the modeling has got the same result. So that is my group doing. But another thing is in China, transport is different. In China, the character is that in the city, point to point in the city, between city, it uses a high-speed railway. Many villages, the third is many villages, small town, use bicycle, 2 bikes, 3 bikes, and now use low-speed, small vehicles. 2 categories of markets. One is in the city, one in the village. In the city, the obstacle is not cost. People, why do not buy? They're afraid, frustrated, stuck on the road because no infrastructure. Second is still not confidence. Thirdly is cost. But in the village, cost is the most incentive. So that is the work of my team. 2030 is the turning point, if according to my roadmap. Then at that time, gasoline will reduce. The total energy for automobile will reduce because it is higher. And among the total energy, gasoline will reduce, diesel will reduce, biofuel will increase, gas will increase, electric will increase, hydrogen will increase. Okay, so when the energy reduce, the CO2 also reduce, And this is the infrastructure, the different sector, okay, different sector, and agree with the former speaker. For heavy duty, long haul, electric vehicle has no economic result. We should use a new liquid fuels. This is my view. Okay. So that is China will have an aggressive plan during this year. It's already jumped. It target next year will reach 33,000, and we focus on the highly polluted. That is in the near Beijing, Tianjin. The other is Yangtze River Delta, Shanghai. The other purely in the Canton. We focus on this. I have to screw up. This is a typical product of passenger car in China. The most popular EV in China. Typical bus, electric plug-in and hybrid plug is China. Structure. I have no time to elaborate this. Several structures. One is a Toyota that is use the planetary gear. Second is four-wheel drive by Volvo or BMW, PSA. Is a four-wheel, front wheel electric, and rear wheel is rear wheel is this. Okay, I must quickly. I have no time to elaborate this. Okay, Tesla. Okay. I have no time to elaborate this. Battery technology. We are moving two steps of battery. First step is double or triple by using NMA or NCA. Okay. Second step is by using the lithium air or lithium air or aluminum air to boost the energy density. I know that you have an invention here on the aluminum cell, right? So we must take care from the material to the production, related to the environment and safety issue. My earlier speaker has addressed this. We must address the safety issue of the motor drive technology, how to make very efficient in the start-stop. So you must be able to design the electromagnetic, the mechanical, the thermal infrastructure. I just mentioned definitely we must use every infrastructure which can convenient. Slow charge, medium charge, quick charge, inductive charging. I just show another inductive charging in China which can be used for online. This is inductive charging in China by ZTE for car, for commercial vehicles, and for bus. The power per unit is 30, maximum 300. The gap is 20 centimeters, and the efficiency is 90%. Okay, so how to interface with the smart grid? Electric vehicle is an indispensable part of a smart house, intelligent vehicles. Electric vehicle is very useful for intelligent vehicles. Okay, no driver. Okay. So it can be interacted with my first speaker today. It is a sensing and actuate. Sensing and actuate. This is another okay, small EV. Okay. Oh, so I say mobility is happiness. Mobility is happiness and freedom. So our mobility should be comfort, ecology, convenience and safety, and we must have success. What is success? Success has 4S, 3S, 2C. Real success is you should throw one stroke, S become American dollars or shekel in Iran. So many shekels, so many US dollars, so many American cents, so many euro is success. The market accepts it. In order to success, we need 6 eyes. I only have 4 eyes. It's not enough. We see the front, foresight, the back, the history, up, the society, the grassroots, and what is the Americans doing, Europe, what is the Japan, Korea doing. 6 eyes, the first eye is inspiration. After inspiration, then you can have imagination. After imagination, innovation. But do not forget, integration is important. Vertical integration technology, horizontal integration society, politics, economy. After integration, then you can implement, but we need investment. Thank you very much.